So yeah, I'm Ben Cumming, I'm from CSCS, and I'm going to be talking about software deployment, software stacks at CSCS. So I've been at CSCS for about 12 years. I joined after finishing my PhD, and I spent the first 8 years as a research software engineer. So I did a lot of work with porting weather and climate codes like the Swiss National Weather Service to run on GPUs, and also doing benchmarking involved in procurements. So that means I was part of that large cohort at every HPC centre that is effectively a glorified user. You know, we don't have any additional privileges that our users don't have in terms of, we have to build and run as normal users on the system. As a software developer working on HPC system, I complained about lots of different things. You can ask me about Python during the lunch if you want. But one of the things that always frustrated us was, why can't we have up-to-date software on our HPC systems? Why is the version of the compiler this old? Or why is, CUDA, this version of CUDA was out 12 months ago? Why can't we have the latest and greatest on the system? We had a reorganization about 4 years ago, and all the people who were responsible for the software stack were interested in exploring some new opportunities. And I thought it was about time to put up or shut up, see if I could actually have a go at working on the software environment, software stacks we provide to users. So ALPS is our current system. Before ALPS, we had a large cluster called Pitstein, and the way that we installed software that we provided to our users. So I'm really focusing on when a user logs into the system or accesses the system, what's the software that's available there for them ready to get started? Whether that's scientific applications or compilers, Python, and some standard libraries for them to build their own software. We did what every large site with a HPE cluster has done and still does today, which is system administrators would put together an operating system image. They would install the Cray programming environment, or the Cray development toolkit as it was called then, on top of that. Now, the Cray Development Toolkit, or CPE, Cray Programming Environment, is prepackaged software that Cray, HPE, put together for running on their system. So that's everything from your basic compilers, their own distribution of MPitch optimized for the network, Python, debugging tools and profiling tools that they provide, as well as your common libraries like HDF5, NetCDF, and these would be installed as some RPMs with some module files on top, and this would be the environment that this would be like what you would call your basic environment installed on the system. On top of that, then CSCS would come in and we would build additional software, common applications for our users on top of that, and then the users would come along and then build their own software on top of that, on the next layer up, or they would just use what we had already provided them, if that was, sufficient for their needs. We were very reluctant to modify the Cray programming environment. So often you'll find that there are bugs or issues or problems in the Cray programming environment. One reason was because you had to be a system administrator. You needed to build a new image. You needed to reboot nodes. So the process of making small changes was painful. It also meant that you had people who were responsible for the software of, working with users had to work with a system administrator. So it was difficult. And we're also a bit worried about if we start modifying this thing, what happens to the support contract with HPE? If they find out that we've been modifying it to work around bugs, are they going to be so willing to support us? So this became quite a bottleneck on how we provided software to users, because CPE would be released every 6 months. By the time it had been finished being tested and ready for us, the software inside it was already out of date, and then it might take us another 6 months, as you're about to see, to then make sure that it's ready to go with all of our users. So if we drill down to why this was difficult for us to do, is that the people who were responsible for working with our users and helping them day to day and installing this extra software we installed, they were effectively glorified users. We don't have root permission, we don't have the ability to change a lot of the things that affect us, including the Cray programming environment. and also updating the system software was very disruptive for the reasons I discussed on the last slide. Because of this, it's part of the OS image. It requires close collaboration with another part of with the system administrator. The iteration time is just very slow. And finally, the vendor is very, very conservative. They want to only release software to us that they are confident has been tested and works. And they tend to be very, very conservative. They lean more towards the conservative side there. We did develop. We're one of the first sites to really put together comprehensive CI/CD pipelines for deploying our software, and we adopted Easy Build very early on, and we made our own regression testing framework to detect errors when we made changes. But all of these on top, they don't address these underlying bottlenecks. So a case study is C2SM. That's the Center for Climate Systems Modeling. It's a large group at ETH, and they've been one of our kind of key users for all the time I've been at CSCS. And their main use case is running atmospheric simulations of the climate and weather modeling. Initially, when I first started with an application called Cosmo, but more recently everything's moved over to using a more modern atmospheric modeling framework called Icon. And each of these codes are very large, complicated Fortran code bases with lots of OpenACC and other goodness in there, and they're very sensitive to changes in the system. If you upgrade the system and change your dependencies, these things are guaranteed to not work the first time, second time, third time you try. They're going to take a fair bit of iteration to get them updated. So the process for upgrading looked like we had a separate TDS, so test and deployment system, a single cabinet with a handful of blades in it that was a copy of our main system PitStite, and we would upgrade, add a new version of the CPE, then the CSCS staff would hop on and provide all the layer that we provide on top. We'd have to upgrade all of our recipes, and then we would get the key users. And C2SM were usually the first ones let on, and they would try to check whether their workflow, whether their software compiled and ran. And we often had to just delay by a long time or just cancel upgrades and wait for the next one, because each new release of the CPE would fix some old bugs, bring some new ones in, and we just couldn't get things to work. So it was kind of a frustrating situation. Everybody upgrades or nobody upgrades at all. So we've now got Alps, which is a large HPE Cray-EX system with a bit under 4,000 nodes with 6 different microarchitectures, like 6 different node types with different types of GPUs and CPUs. And we tried lots of new objectives with the system, but one of the key ones was, instead of deploying a single large cluster with, let's say, Slurm partitions for the different node types, we worked on being able to partition it up into these separate clusters, separate sort of virtualized clusters. So a user doesn't see a single system. They just know that they're SSHing or using Jupyter Hub to access Dint or EIG or whatever we've called one of these dynamically created clusters. And the aim here was that we could target these to specific use cases or communities. So you'll hear later on about a system called Clarendon, which is for the ML AI community. We've got another one called Santis, which is for the kind of climate and weather modeling community. And then we've got, again, a system called Dint, which is more of our general purpose HPC scientific research system. And one of the aims was to kind of have the different communities on these different systems start to take a more active role in supporting their own software stack and providing their own documentation and support to the users in those communities. But the challenge here, like I've just said, the way that we were providing software before wasn't going to scale. So the things weren't going to scale. And I mean, if we sit down thinking about this and also looking back on it retrospectively, we had a few different kind of axioms, a few fundamental truths that we have to acknowledge. The first is that HPC centers provide pre-built software for our users. We did have some people saying, oh, why can't we just be like AWS? You jump on, you get a bare bones system, and you have to bring all of your own software. Or just let people bring containers. They can bring containers in from the internet and just run them on the system. But a large part of our of our service offering is pre-compiled, pre-built, pre-packaged software ready for our users to use. There's a lot of our users who we would be cutting out a large part of our user base who aren't comfortable with just jumping onto a bare bones system and building up a software from scratch. So we need to do that. Vendors can deliver some good software stacks, but they can't deliver a software stack that's going to meet the needs, like a single monolithic stack that's going to meet the needs of all of our users. Another thing is that scientific projects typically have a 1 to 3 year lifespan on our system, from when they start to when they finish. And you want them to be able to build the software, set up their workflow once at the beginning. Often that can be quite a painful process for them. Once they've got that set up, ideally they'd not have to touch that for the lifetime of their project. You want to minimize the disruption there. We've got other developers and some communities, MLAI users, anyone who's using Python heavily. Typically they want to be able to, it's not even just update frequently. Often it's more like a rolling release model that they like to follow of just, I just saw, we had a ticket from somebody who was, this morning, who was using some rolling release system for deploying AI stacks. So every time they rebuild the container, they get some new all-in-one package. So we've got these different communities moving at very different speeds is the key point here. The staff who install the software and provide support to users have to have full control over that entire stack. We can't have them having to go off and get someone with root permission to modify something for them. And software installation should not, to provide a new version of software, we shouldn't have to touch the running system or interrupt users in any way. That seems kind of obvious, but actually if you look at how we've deployed software on HPC systems in the past, that's not at all how things have been done. So I'm not going to get into technical details here, but I mean the first thing we did was we said, right, we need to be able to build from the ground up. If we're not going to use the Cray programming environment because it's not a stable foundation, we need to be able to build software stacks from the ground up. We created a tool called Stackinator because naming things is really hard. I apologize for that. Each software stack, so we might build a software stack for GROMACS or a standard kind of programming environment or an MLAI kind of PyTorch-based environment. They're based on a basic YAML recipe, and we have separately, so the recipe shouldn't change, but the clusters, the configuration underneath, will still change. So we separate the description of the clusters from the recipes, and then with the Stackinator tool basically takes those two and generates a make file. It's a bit like running CMake. CMake gives you the recipe. Then when you run the actual CMake command on your system, it goes and finds all the dependencies and comes up with the concrete recipe for building the piece of software. This is a similar level of abstraction. The key point here is then that the make file, at the end of this running this build process, we get a single squashfs file. So squashfs is basically you compress a directory into a single file, and squashfs gives you the machinery to efficiently mount that as a file system at a specific location. And we only have really one dependency that's installed at the system level, which is libfabric, the low-level communication library used by Nickel and Cray and MPI and other communication libraries to do the internode communication. We don't have like a single version of SPAC everyone has to use. That's per recipe. And here's just an example on the right of the recipe that provides the software for ICON, which is this weather and climate application. The second part is to make using these software stacks convenient or very easy. And for that, we provide this UN command line tool, which you can think of as like being the simplest, most lightweight container runtime. It doesn't do any chur root. It doesn't try to change the file system. All it does is it mounts the software at a fixed location, and then it also modifies the environment. So it provides machinery for modifying the environment variables. And you can also manage your images, the different UN in a local repository on the file system. So from the user's perspective, they start one of these things, and if they look closely, they'll notice, hey, there's some software has appeared in a directory where there was none before, and some environment variables have been set, and things just work. So you can see here, this is me getting a list of all the images that are available on that cluster that I'm logged into, and then starting one of them, and you can see that your compilers, your CUDA and MPI are now available. And this thing is really simple. It's not trying to do anything more than it has to do, and this means we're able to implement it really quickly, and once we had it implemented, it hasn't broken yet. Whereas if you try to do something more complicated, we go, let's go for a full container runtime, then there's a constant battle against entropy on the system as things change, and you try to keep that container runtime up and running. We've also got a Slurm plugin. I won't spend too much time on this, but we had to kind of follow the principle of least surprise. I mean, it was a good point earlier about users not really knowing how computers work. They particularly don't quite understand how they work when you're on a HPC system, where you log into a login node and then you go srun or sbatch, and what's the difference between a login node and a compute node? And when they load a module, they log in, they load some modules, and then they run a job, that they're used to that kind of environment magically following them around onto the compute nodes, for example. And underneath the hood, Slurm is doing a lot of kind of heavy lifting there to try and make sure that what you see on the login node matches what you get on the compute node. And we tried to follow that same principle. I think Slurm integration for things like container runtimes is basic table stakes now. It lets you be much more efficient, and it lets you do things like keeping track of what your users are running, which has always been traditionally one of our big challenges. I'm going to quickly stop to mention another service that we provided for users, which is our CI/CD service. We wanted to get more users and more developers of applications running CI/CD on our systems. So we figured, well, it should be as simple as setting up like a Travis CI or Circle CI, or these were the predominant kind of external CI providers at the time when we started working on this. Minimal configuration, have a YAML file inside your project, and then when you do your pull request or your merge, there should just be a little green, there should be the traffic sign light on the commit in GitHub. People shouldn't have to kind of follow a magical link to go to some other page to see what the status of their build was. So we created this machinery because we wanted to give the users a really good, nice experience there. And because we made this really user-friendly and we made it so that users could use it without having to talk to someone, to another part of CSCS, it started to kind of cannibalize a lot of our CI/CD machinery inside CSCS. So we also use this for deploying, for the next step, which I'll talk about, which is how do we build and deploy these images. So deployment is, we have a GitHub repository that has all of the recipes for the different UENV that we want to provide to our users in there. And we have the CI/CD external service there configured to do the builds, because we're not just building software for a single cluster. We've got all these different clusters that we've partitioned this one large system up into, with all these different microarchitectures. So there's a bit of machinery underneath there to make sure that when someone makes a pull request to add a new image, that it gets built on the right cluster targeting the right microarchitecture. And we do that. We use a tool called Auras, which is a nice kind of tool it's a piece of software that lets you push arbitrary artifacts into container registries. Container registries can be used for storing more than just containers. So we've got an internal container registry at CSCS that has, once the image has been built, it's kind of stored in there, and then we can also pull the image from there to run reframe tests. Deployment, like when we actually make it fully available to users, is still a manual process, because we still find that often you do want to give this image to some users to let them try it out first before you do the final sign-off. And we've got support for things like, in the past, software like VASP has got a very restrictive license. So we provide VASP on our system because it's pretty horrible to build. and lots of our users use it, but our users have to show us that they have a license for VASP, then they get added to a special group. We would install the software in a directory that only that group could access, and that's how when only the people who had the licenses were able to use the software. Now we have to use tokens to permit, give people selective access to tokens for downloading the software. So if we go back to this, there's a lot of work underneath here, but I'm just giving you like a very high-level overview. So if we go back to our original axioms, I mean, we are providing software to our users. We don't have much control over the vendors, not nearly as much control as we'd like to think we do. We haven't been using this, we haven't been really using this in production for 3 years, so I can't say for sure that we're able to support applications for 3 years, but we've got images that are 3 years old and they're still working, and so far we've not had any problems with system upgrades breaking users' workflows. But we can also we can very quickly rebuild, because we're using SPAC underneath to do all the rebuilding, so as long as something's in SPAC, or we can add our own custom package to SPAC, we can actually turn around and provide software very quickly. We've got access to an RPM repository from HPE where they put the nightly builds of their Cray-EX and their communication libraries. So now we can actually roll those out, the next day images with those nightly builds. So we can deploy it much faster than if we were actually deploying things through the CPU. So, and now the staff, these stacks are built completely in user land. So yes, the staff can build them by hand, they can use the CI pipelines, and also users. Now we've got more and more users who are starting to build them. And the final thing is these are just artifacts getting pushed into a container registry. So they make no changes to the underlying system. Users have got a list of images that they've downloaded, just like you would with a container runtime. They can try out the new one. If it doesn't work for them, the old one's still there. Their workflow doesn't change. So we don't interrupt anybody. Now, if we look at what happened with the climate weather platform, I mentioned this earlier, they've got a system called Scientis, and C2SM, this climate systems modeling group at ETH, they're one of the main partners with this, along with Meteo Swiss, the Swiss Weather Service. And initially, it was basically my job, because I started providing the software to Meteo Swiss. It was my job to define the different environments and build them, deploy them, test them, do all of this for them. Once these guys got used to using the UEnv, they started to ask more and more questions about, can we build our own UEnv? And I always had plans to create a separate pipeline for them, give them the keys to that only gave them the right to push the images to their specific clusters. I mean, it was actually them who ended up harassing me into finally getting around to creating that pipeline for them. So now we've actually got these guys who used to have to wait for us and get very frustrated with us, and then they would hold us up. Now they're actually kind of taking full control of their software stack, which, that's a pretty big cultural change when you've got these groups that have had, this history of depending on you to get them to actually change around to really wanting to take responsibility. And we've also got a lot of smaller communities, small labs are now visiting and asking, how can we set this up so that we can just start, because often you'll have a lab or a place where there's 1 or 2 staff who actually provide the software to all their users internally. So we're starting to get more and more people using the software and this process. So if I was to have a retrospective here, we focused on empowering our glorified users, i.e. just the staff who didn't have root access. I was really focused on how do I help people like I used to be, the research software engineers, and how do I address the main pain points internally. But we ended up helping our users because we created tools that helped all users basically. And empowering means both giving people the responsibility, but it also means giving them the tools and the processes that don't suck. And there's a lot of software building processes that we use in HPC that are pretty awkward. And we really managed to achieve one of our key objectives, which was to start getting user communities to take more control for more parts of the what you would call the service, the software stack, and so on. I'd like to claim that I'd like to say this was part of some clever master plan. It wasn't. I was really just focused on internal users, but after a while it became apparent that this could be something that we could actually use to start getting into the hands of our communities. Final note, on documentation. Documentation is the next thing I'm looking at because our current user-facing document is on Confluence, and this is not a great way to do things because only CSCS staff can modify those documents. And we've got a slightly unfamiliar and awkward workflow if you've tried to use Confluence to have an offline version that you can then promote to production. It's not a very elegant or familiar workflow, and this is my own personal opinion. I don't think the docs are great as a result. And I've noticed that we've got user communities who have gone and creating their own parallel documentation hidden away in markdown files on GitHub repositories. So we are moving to a GitHub repository where we deploy everything using CI/CD with proper preview documentation generated. We're using familiar tools and workflows, give people GitHub, add reviews, add markdown, give people things that they're familiar with. And also the infrastructure for defining what the docs look like and how they deploy it's in the repository, so everyone can contribute to that. And we've got much more enthusiastic engagement that I've seen so far from staff on this. But the open question is, can we actually, if we do structure the docs right, will people actually come from outside of CSCS and start contributing to them? So on that note, I will finish on time.
Thank you, Ben. We have time for a question. Okay.
Yeah.
Thank you, Ben. Cumming.
Normally I get one person asking, why didn't you just use containers? But, not today.
Oh.
So if the UM environment, if you want to produce it on a system outside Alps, how would that be difficult, possible? What are let's say, the most important requirements?
It's possible. It's a bit of a pain in the neck. We built this tool, like one of the key things was we wanted to remove as many options, configurability from the tool. We made it Alps specific, and that's why it's basically me and half another person looking after the whole thing without going crazy. It's possible to build offline. You've got to know a couple of tricks, but I'm quite resistant to making it into a generic tool because then I go use a container.
next presentation comes from Alessandro Ragazzi from HPE, who's going to give an update on their Smart Sim strategy.
All right, welcome everybody. Good afternoon as of now. So yeah, my name is Alessandro. I'm a research engineer at the HPC AI EMEA Research Lab in HPE. And today I'll be talking about Smart Sim and its last evolution and changes in strategy. So for those of you who weren't here last year or don't know what Smart Sim is, I'll just give a brief introduction. It drives along with what's already been said today about the evolution of HPC, simulations, and AI. So over the last, I'd say, 5 to 10 years, we've observed a paradigm shift in HPC. So the old numerical workflows used to be quite simple. You used to have input data, so initial conditions, could be a file, could be hard-coded values. And then you would have this monolithic application, which was like your code you have been developing for 10, 20, 30 years, always updating it with new things you could think of, new algorithms you were finding in the literature. You would just add it to your old C, C++, or Fortran code base, and you would just make sure it works for your use case and then move on to the next thing. And then you would execute the code on your input. You would just get the output. The output would be then a file. You would store on the file system. You would analyze it once, maybe twice, visualize it, put it in a paper, present it. That's done. And that was good as long as everything was more or less moving at the same pace, especially numerical algorithms and research were moving at the same pace. But now there is AI in the mix. And AI, as you know, evolves at a very different pace, at a very different rhythm with respect to numerical algorithms and methods. And so now what is more useful to have is a composed workflow where you have, obviously in our case, so we're like what we are developing is something just targeting numerical workflows and HPC simulations. So the core of the engine is always for us the HPC parallel application, so your standard MPI, C, C++, Fortran-based simulation. But then you want to add something new, some new method you found in the literature. It could be ML inference. And now I'm not much of a proposer of replacing the whole simulation with ML inference. I like to think that ML inference can fill the gaps and the blanks you originally filled with approximations or just heuristics or just parameterized models where you just estimate some parameters which your model wasn't capturing, for example, right? And you want to replace that with a machine learning model. Or you want to train the model while your simulation is running. That could be a use case in which you don't want to store all the data you're producing because it's too large and you just want to train the model as you run the simulation. Or it could be something like reinforcement learning where you want the simulation and the training to move together. And then maybe you want to do visualization and analysis. So all of this doesn't work if you use the old numerical workflow, old way of writing code, because you want to be able to separate concerns and have like the HPC parallel application just doing the simulation, the ML inference just doing the ML inference. So just using the best you can find about AI models, for example. So you want to just grab the new version of PyTorch, the new models from Hugging Face, and put it in your workflow, right? So you want to have a separation between the two things. You want to do the same thing for model or for the visualization, right? So what we tried to develop at the beginning, like 5 years ago now, was a way of orchestrating very lightly this whole workflow just by allowing a clear exchange of data. So SmartSim is our solution, and it's an open source library. It's totally open source. It's on GitHub. There's no secret sauce. Everything is there. And it tries to bridge the divide between traditional numerical simulation and data science, right? It does so by putting a database, an in-memory database, starting it, and then informing all components of your workflows about its existence, so that then by using our clients, which are super lightweight and very easy to use, every portion of your workflow can communicate with the database. The database is a feature store, so it can also store active code, scripts, AI models that can be executed directly on the database or on the feature store. Currently, it uses Redis as a backbone and Redis AI for executing AI models, but we are moving on from that in the future or in the near future. And what SmartSim enables you to do is using machine learning models in your existing simulations, like in Fortran, C or C++, or even in Python, obviously, exchange data across the boundaries of language and simulations, and train machine learning models or analyze data streamed from your application in real time. All right. So again, the idea was just to allow embedding machine learning into C, C++, and Fortran simulations, right, and exchange data at scale, right, without touching the file system. And the reason I say this is because as every numerical software developer turned AI scientist, at the beginning I was just saying, okay, let's just run one step of the simulation, dump everything to disk, read it from the AI script I have, dump the inference result to the disk, read it back into the simulation, and that would kill every file system I know of. And that's what many people still try to do as a first attempt. And then they're super surprised when you tell them that if you use an in-memory file system or in-memory database or also a file system, it gets much faster, right? So they test it and they say, oh, well, we have a 20% or 30% speed up by doing basically nothing. And it's obvious because you don't touch the file system anymore and you don't misuse the file system for something it wasn't thought for. And so there are some updates on SmartSim. There's an updated structure, but we start from an old mission. It's always to help scientists and researchers, right? So we just want to empower our users and our community to write modular workflows which can be ported across systems, across workload managers, and across different architectures. But we are now more open. So SmartSim is still maintained and updated by HPE, so we work on bug fixes and stuff like that. But we're more open to external contributors. So in the past, we would talk to users, we would organize hackathons and stuff like that, and then we would just gather all the suggestions, implement them, and then give them to the users and ask them to review them and see if it was the right way of implementing them. Now we are more open to collaborations, and this comes as a result of some very, very good collaborations we've had in the past, where we have seen that the results were incredible and very useful for other users too. And so we develop new features when the users request them. We are not pushing new features unless the community is asking for it. And then SmartSim has moved also in the organization, in HPE. So it was moved from the HPC and AI software group to the labs organization. So now it's incubated by the team I'm part of, so the HPC AI EMEA Research Lab, and it's co-developed with an HP lab in the US, right? So it's like we have another developer on the other side of the Atlantic Ocean. So talking about the new house, this is the HPC AI EMEA Research Lab summary slide. So we are a lab. A lab is an organization which doesn't really push for selling new products as a first thing. It just does research. Our role is that deep technical collaboration with industry, academia, and public sector, long-term technical relationships, and focusing on new technologies, and then driving future HPE products. All things that work very well with SmartSim's philosophy. And then our research interests are also very well aligned: HPC, cloud, AI, and quantum, data movement, analysis and workflows, heterogeneous computing, and novel accelerators, things that we've always tried to support with SmartSim. And we have different engagement models, for example, the centers of excellence and advanced collaboration centers, and then ad hoc projects, and so on and so forth. So I'm part of one of the advanced collaboration centers. I'm part of the LUMI one. We have one with Archer 2, KAUST, GW4, Lumi, Blue Lion, and also one in Australia with Posey working on Cetonics. And for each Advanced Collaboration Center, we have different projects. Sometimes their goals align, sometimes they diverge, and we try to work in strict collaboration with their engineers. And now let's move to a more applied use case of SmartSim. So this is one of the latest, not the last, but one of the latest research paper which use SmartSim. It was published by Bernard Font and others. Most of the simulations were run on at the Barcelona Supercomputing Center. So it, again, as I was saying, the cool thing about SmartSim is that it separates well the simulation and the AI part of your workflow. And this is something very, very good when you want to do, for example, reinforcement learning with HPC simulations, as they did. So the idea is to do active flow control of turbulence separation bubble through deep reinforcement learning. So kind of the big picture. So imagine the plot on the right-hand side to be the profile of a wing, or a simulation of a profile of a wing profile, where you have the bump, which creates a difference in pressure, which then creates detachment and reattachment of the flow, which in turn creates separation bubbles and recirculation. And wherever your flow doesn't flow well and recirculates, you have drag, you have loss in performances, right? And so the idea of the study is to reduce the turbulence separation bubble formation. And they did this applying reinforcement learning, which is something we've seen many times done with SmartSim now. I mean, I think it's the third or fourth group which uses SmartSim exactly for this. So we're very happy that it's kind of spreading in this CFD reinforcement learning community. And so you possibly already know what deep reinforcement learning is. If you don't know, I'll just give a quick recap. You're training an agent, right? So something that has to interact with an environment. If it's deep reinforcement learning, it usually means that you're using a deep neural network as the way the agent decides on what to do, what action to take based on the environment to optimize some reward function that you are defining. And this is cool because in other studies we've seen the same exact environment giving completely different results when they change the reward function. In this case, obviously, they wanted to minimize the recirculation length. So this is just basically a way of characterizing your turbulent bubble. They want to minimize the recirculation area. And yeah, the environment is just composed of 72 probe points. So basically 72 points where you can sample the flow. And then, yeah, they trained on 24 parallel pseudo environments on 8 GPUs. So on each GPU, you have multiple environments. And in more or less a week, they were able to get the training done. How they achieved this? Well, the simulation part. So the workflow was launched through SmartSim. SmartSim is So SmartSim has an infrastructure library, which is a Python library, which allows you to interact with the workflow, with the workload manager and the launcher you have on the system. Usually you do it in a Jupyter notebook or in a Python script. So the whole thing was launched through SmartSim, and then SmartSim would launch the simulation on the different nodes, the in-memory database, again, it's a Redis in-memory database in this case, and then the reinforcement learning model running on different nodes. And the simulation and the reinforcement learning model will just put and get data from and to the database, right? So at each step of the simulation, the state would be put on the database and it would be accessed by the reinforcement learning, or trajectories would be accessed, and then the reinforcement learning model would be trained based on the reward function. And so the results are pretty impressive. So this is what happens if you don't try to control the flow. Then in the state of the art, the idea was to put these 6 actuators, which can basically suck or push the air, basically, around them, right? And the state of the art was to use them periodically. So, you would just add some periodic push to the flow, and this would reduce, for sure, the average recirculation length, but it would also start creating these large oscillations, which then could be actually detrimental for your whole flow and the stability of your, for example, wing. Whereas with deep reinforcement learning, they were able to minimize the surface much better, and especially if you look at the right-hand side here, the far right plot, you see that the average is lower and the peaks are much more contained, and this is very important. So they were able to reach a 25% reduction compared to the 15%, which was in the state of the art. Finally, the project I was talking about, where we took the inspiration for the new structure of the SmartSim project, was the OpenFOAM collaboration. So we teamed up with the OpenFOAM data-driven modeling special interest group. OpenFOAM, for those of you who don't know, is one of the most widely adopted open source CFD solvers or library. And we've teamed up to create a submodule, so OpenFOAM operates with modules and submodules that allowed users to seamlessly use SmartSim and our database from the simulation using basically the typical OpenFOAM syntax, right? So we published a paper about this, right? And in the paper, we use SmartSim with OpenFOAM to achieve 3 different types of interactions between AI and numerical simulations. And the submodule was actually accepted by the board, the OpenFOAM board. So it's the official submodule used by the OpenFOAM community to use machine learning in OpenFOAM right now. It has 3 layers, and this was something that came out from the collaboration. So it has, I will just go a bit quicker than usual on this, but like there's the service API, which is the higher level API. It's just, you can just do more or less one thing. You can just send these geometric fields, which is the way OpenFOAM sees data and fields, to the database, and you can get it back from the database. And then you can do not much more, but this is usually enough for the basic workflows you want to achieve when you do, for example, CFD in reinforcement learning. Then there is a bit lower level is the developer API. So they don't interact directly with Redis database. They handle what is called a data set. In SmartSim, a data set is just a construct which keeps all tensors together when you push them to the database, which can be running on any node of your system. And then there is the lowest level, which is the generic API, which is more or less just a one-to-one match with the SmartSim API and SmartRedis API from the OpenFOAM library and language. And so one of the cool things about using this approach where we completely decouple the simulation and every other portion of your workflow is exactly this, that by defining the way you want to communicate, what you want to communicate to the database, then you can put the database on any node of your system. You can maximize resource utilization by using nodes which are best suited for your database, for example. Maybe because you want to run AI in the database and you don't want to run it in the simulation itself, so you will just put the database on the GPUs and run the simulation on the CPUs, right? And that's what's basically enabled by these kind of interfaces we hope to replicate in other libraries too. Okay, I don't think I will go through the recap because this was quite short, but again, everything is available in a public repo, right, for the submodule, so you can download it and use it in OpenFOAM, and the paper which was published and it's open access shows exactly how to use the module and different examples on how this can be used to achieve modern workflows. Finally, we have a very, very good documentation. I am very proud of it. It's hosted on craylabs.org. It gives basically, it has the API and many examples on how to use the container and so on and so forth. So you can just go and browse it yourself. Otherwise, there are many resources. You can always send us an email or go through the repository, or there are some case studies published and so on. And if you go on the repo, don't forget to star it. That's it. Thank you.
Thank you, Alessandro.